So, hi everyone, we'll see indexes in SQL in this video. So, first of all, let's understand the indexes in layman terms. On the left, we can see there is a person who is very overwhelmed by a mountain of papers, who is struggling to find a specific document, which actually represents how a database works without indexes. If we do not have any index on any piece of paper, then we have to go through each and every piece of paper in order to find the desired element, right? So without indexes, the SQL database looks similar to this. And on the right, we can see the same person is efficiently filing and retrieving the document from a filing cabinet. Like each drawer and each folder could represent an index and helps to organize and locate data very quickly. So, just as a person can go directly to the right drawer and folder to find a document, an SQL index allows the database engine to quickly find the data it needs without scanning the entire table. So, it would obviously result in a much faster query performance. So, basically, an index is a special database object which is designed to improve the speed of data retrieval operations in a database table. It can basically be compared to an index in a book, which allows you to quickly find the necessary information without reading every page. That's why our books have indexes in order to save time, in order to save resources, right? So, how does an index work? Basically, an index is stored in like a data structure, which is like a binary tree or a hash table, which allows us to do faster searching and faster retrieval. So basically, as you can see in this image, basically when a query is executed, the SQL engine can use these indexes to find data quickly without scanning the entire table. So it will reduce the number of disk accesses required, as indexes provide a shortcut to the location of the data. So, for example, we can see over here, if we have to find an element which has an index 80. This is how binary tree works for indexes. First of all, we'll start at the root level where the range is from 1 to 200. Then for the next level, for the intermediate level, we'll decide like between which range our element lies. So our element, which is 80, it lies between 1 to 100. So we'll go at this node in on this level, and then for the next level we'll do the same thing. We'll decide between which range our element lies. So for the next level we'll go between this range 51 to 100, and the leaf level, which is the last level where we're gonna find our element. For this level we'll again decide between which range our element lies, and then between 76 to 100 we'll find a element which has index 80. So the leaf level, basically we have index nodes, right? So for example, let's take a customer's table which has ID, first name, last name, email, phone number, address, city, state, postal code, country, date of birth, and registration date, and see how our indexes work. So let's discuss about the types of indexes. We have clustered indexes, non-clustered indexes, unique indexes, and composite indexes. Let's see these one by one. So for the clustered indexes basically sort and store the data rows in a table based on their key values. For example, we have to create a clustered index or customer ID table where we are going to store the customer records in order of their IDs. So to create that, we'll write the query create clustered index, the name of the index on customers, which is the table name, and customer ID, which is the column name. So basically, it will store data rows sorted based on their key values. So because of this physical ordering, each table can have only one clustered index. We do not have multiple clustered indexes in one table. We just have one clustered index. So what's the use case of this? It's ideal for columns frequently used in sorting and range queries. So for the non-clustered indexes, we have a structure which separates the data rows and include pointers to the actual data. A non-clustered index on last name would help speed up queries searching for customer by their last name. So for example, in the customers table, we have to search for a customer by their last names. We can use non-clustered indexes. So how to create them? We can use the query create non-clustered index on this, the name of the index on table name and column name. So for characteristics, they contain pointers to the location of data, A table can have multiple non-clustered indexes. Unlike the clustered indexes, we can just have one clustered index and multiple non-clustered indexes. So basically, non-clustered indexes are useful for the columns which are used in search conditions, but not in sorting. So as we uh, as we can see that clustered indexes are best for the columns which are used frequently in sorting and range queries, and clustered indexes are ideal for primary key. Also, like non-clustered indexes, they are suitable for columns used in search conditions but not in sorting, and they are effective for columns used in joins and where clauses. So let's see what are unique indexes. Unique indexes ensure that all the values in the index are distinct. We cannot have the same values if we are using unique indexes. For example, on the customers table, each and every customer would have a different email ID. So we can create a unique index based on that email ID. So to create that, we can create unique index on the email ID on customers and email column, right? And it will ensure the uniqueness of each value in the index, and they are often used to enforce constraints like unique keys. So these are basically ideal for the column where each value should be distinct, like we have email addresses. So as we can see, it is a little bit similar to clustered index. So what is the actual difference between clustered index and unique index? Clustered index defines the physical order of data storage in a table and can only exist once per table, as it directly sorts and stores the table values themselves based on the index columns. But meanwhile, a unique index ensures that all the values in the index are distinct. All the values in the index are distinct, which will prevent duplicate entries in the index columns and can exist multiple times in the table for different columns. So basically, if we look through it, then the primary purpose of a cluster index is to organize the data storage for the efficient retrieval. But on the other hand, unique index primarily enforces data uniqueness within the table. Now, let's see what are composite indexes. Composite indexes are built from more than one column, and they are useful for the queries involving multiple columns. Example, if we can see, then we can create clustered index on last name and first name. Sorry, composite index on last name and first name. So composite index on last name and first name can optimize searches that involve both of these fields. Unique indexes can only exist on one column, and every value should be distinct. But for composite index, we can use them in a you know like use them in multiple columns, like in a group of columns. So they are beneficial when queries use multiple columns. They are ideal for improving performance in queries that involve several columns. So let's see what is the difference between non-cluster index and composite indexes, as they sound similar. So like non-cluster indexes are about having a separate index structure for each column, and composite indexes are about optimizing queries that involve multiple columns. So how are we going to manage the indexes? So to view the existing indexes, like the indexes we've already made, we can use the query select star from this sys.indexes, where object ID is object ID and table name. So in order to view SQL indexes, we can use this query. And in order to modify and drop the index, for modifying, we can use the alter command. Alter index, the name of the index on the name of the table, rebuild. We can use the rebuild command and we can write the new query of index that we want to add to the table. And in order to drop the index, we will use drop index name on table name, on the table name. So when should we use the indexes? We should use the indexes when querying large data sets, when we have like a lot of columns, a lot of tables to go through. We can use indexes. We should always be mindful of write operations, as indexes can slow down. Like if we use indexes on inserts, updates, and deletes, the query will slow down, and it will reduce the performance of our code. And we'll consider the column's uniqueness and query frequency. There are some common pitfalls and misconceptions about the indexes. Let's see. First of all, there's over indexing. Like, as we know that indexes can improve read query performance, but having too many indexes, it can lead to decrease in performance, especially for write operations like insert, update, and delete. Each index in the table needs to be updated when a data modification occurs. Each index needs to be updated, right? If we do any data modification in the table, for example, if we have to change the last name to something else, or we can, if we have to change, if we have to remove the phone number from the table, then we need to update the indexes, like, which will lead to longer processing times. And if we use indexes on the small tables, they're not that effective, because the SQL engine may bypass the use of indexes for small tables. Because if we can, like, we'll have a primary key on a small table, then we will not gonna need indexes. We just need indexes in large table in order to do a quick performance on our code. But for small tables, we can just simply, go through a number of columns. There are very limited number of columns, and we can go each through each one of that would be faster than using indexes. So for smaller table, the indexes, the SQL engine would bypass the indexes, and it will not be justified. Like, we can do a full table scan in order to find a element. So in small tables, the performance gain from indexes is minimal. So that's all for this video. Thank you.